Welcome to day 1, trimester 2 of calculus. We're going to start by talking about exponential functions. Those are functions of the form y equals a times b to the x, where a is the initial, the starting value, and b is equal to 1 plus r, where r is the growth or decay rate. And you have growth when b is greater than, when b is greater than 1. So that's going to happen when r is greater than 0. And you have a graph that ends up looking like this. It grows like that. And then if b is between 0 and 1, which means that r would be less than 0, you have decay like this. You have decay. So that's the type of graph we're going to be looking at. A common question you could be asked is find an exponential function given some data. And in this case, we're given 2 points. The first point is, well, f of 1 is 300. That means you have the point 1 comma 300. And the second point is f of 3 is 675, meaning the point is 3, 6, 75. We are searching for a function y equals ab to the x. So let's take these 2 points. Let's take these 2 points and plug them in to get 2 equations. So first we know when the output is 300, x was 1. And when the output is 675, x was 3. So you have 2 equations and you're solving for a and b. You want a and b. So what you can do at this point is you can divide these 2 equations. So when you do this out, let's divide this one right here. Let's move it down here. You can take this. I'm going to move it down here. I'm going to put it right there. So like AB to the first. And I'm going to divide these 2. You can do it either way. I just want to do this to a number on the left greater than 1. When you divide, so we're going to divide both sides, which we can do because both sides are equal. 675 divided by 300 is 2.25. And right here, the a's cancel, but over here, b to the third over b to the first is b squared. So we now know that 2.25 is equal to b squared, so you square root it, so b is equal to the square root of 2.25, which actually comes out to be 1.5. So now we pause and we say, okay, so b is equal to 1.5. Let's plug that in and we get y equal a times 1.5 to the x. Now we need x, and we can find x by just taking one of these points and plugging it in and solving for a. So we know 300 is equal to a times 1.5 to the first. So a will be 300 over 1.5, and that is 200. So now we have our a value right there. So we plug it in and we end up with y is equal to 200 times 1.5 to the x power. So let's answer some questions about this equation. Is it growth or decay? Well, b in this case is 1.5, which is greater than 1. So therefore, that's what the 3 dots mean. That's growth. If b is greater than 1, it's growth. What's the rate? Well, b is equal to 1 plus the rate. And in this case, it's 1.5, 1 plus r. So r is equal to 0.5. So the rate is 0.5, but a better way to say that would be our growth rate would be 50%. And what's the initial value? Well, the initial value is what is the value of y when x is 0? So what happens when x is 0? Well, it's always going to be the leading coefficient right there. And you can see that because y equals 200 times 1.5 to the 0 power. 1.5 to the 0, that is 1. So you have y is equal to 200. So our initial value is going to be 200, which is the initial coefficient, the coefficient out front. So now let's move into some fun exponential growth and decay problems. The half-life of an element is how long it takes for half of it to decay. So no matter what you start with or where you're at, this would mean, this statement, the half-life of a radioactive element is 3,200 years. It takes 3,200 years for half of it to go away. Find the time it takes for an initial amount to decay by 35%. So we're still looking for this a, b, and I'll call it to the t because it's time in this case. We're still looking for an equation. We need an equation. So when you say decay by 35%, how much is left? If something decays by 35%, how much is left? So if you started with 1 of something and you decayed by 35%, you would end up with 0.65 of it. If you started with 1 of something and you decayed by 35%, you'd end up with 0.65 of that. You can start with 165 if you want, but this is fine. So what this means is you will have 0.65 equals 1, the initial value, times b to the t. We're trying to find the b value here. And the way you can think of that in more general terms is if you started with A as your initial amount and you decreased it by 35%, that would be 0.65A. So you could start more generally if you wanted to. You could start with 0.65A, which is how much you're at, equals A times B to the T. Well, what cancels in that case? The A's, and you're still left with what I had before, which is 0.65 equals B to the T. So now we're trying to find what that B value is. So we'll circle this for now and search for B. We need B. We definitely need B. So we do that by using this. The half-life of the radioactive element is 3,200 years. That means after 3,200 years, only half of it remains. So if you started with A and you went 3,200 years, you'd end up with half of A. So what that means is you're going to have half of A after you've gone 3,200 years. So after you've gone 3,200 years, you have half of A remaining, half of A remaining. So if you were to do this, A's cancel, you have 1/2 is equal to B to the 3,200. And that's one variable, so we can solve for B. And we do that by taking the 3,200th root of 1/2. So B is going to be equal to the 3,200th root of 1/2. You might ask yourself, how do you type that into your calculator? You do that by doing, you can do B to the 1 over 3,200. So it would be B times 1/2 to the 1 over 3,200 power. So you definitely need a calculator. So when you do that on your calculator, you'll get something like this, 0.999783415. And that should make sense because if it takes 3,200 years for something to decay, it's going to decay really slowly, really slowly. So now we can take this value right here. We could take this value right here and plug it in where we need it. And that's going to be right here. Remember, we needed that B. So now we have 0.65 is equal to this thing in blue here, that thing in blue. I'm going to call that cap. Well, we can just put the decimal in there. That's fine. So 0.9997. And I'm going to store that on my calculator because in this case, it seems really important that we have all those decimals in there to the T power. To the T power. So I'm going to my calculator right now and I'm storing this blue B value because I really want all those decimals. So what we're solving for here is this T value, which will tell us how long it takes for it to decay by 35%. So now this is an exponential equation, so you need to turn it into a log equation, and that's going to be log base 0.9997 of 0.65 is equal to T. And how do you plug that into your calculator? Well, that's going to be T is equal to log of 0.65 over log of 0.9997. So, and remember, you need all those decimals. It's really important you keep those decimals. So when you do that, you end up with 1,988.76. And this is in years. And that should make sense because it takes 3,200 years for half of it to decay. So how long would it take for 35% to decay? Well, it should be less than 3,200 years, and that's correct. So what we did here is we started here and we used decay by 35% to make the 0.65 there. So we ended up with this, but we needed B. To get B, we use the half-life. So if A turns into half A, that half A goes there, the A's cancel, and you're left with 1/2 equals B to the 3,200, which is the half-life is 3,200 years. And then we used our calculator to get this big decimal. We plug that into the B value right there, and we get this equation. And then we need to solve for T using the rules of logs. And you might have questions about that, so please ask that in class. So let's look at this next question. It says the population grows by a total of 30% every 5 years. Find the doubling time to the nearest month. So what does that mean? Well, at time 0, let's say there were 100 people. So at 5 years, if it grows by 30%, that's multiplying by 1.3, is growing by 30%, which is 130. But then if you're at 10 years, you're going to have 100 times, oh, it's not 100, it's now 130 people, and it's growing by 30%, so it's 1.3, and that's going to be 169. And then at 15 years, you're going to have 169 times 1.3, which is 219. So if you had to make a guess here, take a look. If we started with a population of 100 and after 15 years we got to a population of 219, our guess, oh, I'm still in highlighter, our guess should be less than 15 but greater than 10. So maybe 13 years. So that's just a guess based on a table of values, but we want the exact time. Again, we're trying to find out when the population doubles. So the population turns from A, it's not A, I'm writing 2 here. The population turns from A as our initial to 2A. So that means the equation we're looking to solve is 2A equals A times B to the T. And just like before, the A's cancel, leaving us with 2 equals B to the T. But now, just like before, we need that B value. We need that B value. And we find that because we know every 5 years, it grows by 30%. So what are we going to do? Well, in 5 years, it goes from A to 1.3A. So we know 1.3A is equal to A times B to the 5, because this is the growing by 30% every 5 years, growing by 30% every 5 years, just like what we did before. The A's cancel, leaving it with 1.3 equals B to the 5th. So B is equal to the 5th root of 1.3. You need your calculator for that. If you wanted to get the decimal, you get this big long decimal that you definitely store in your calculator, which I'm doing right now. I'm storing it as letter B. And we now do the same thing we did before. We take this number right here and we plug it into the B right there. So when we take that number and plug it in, we end up with 2 is equal to 1.0538 to the T. So we need to solve for T. That's an exponential form. So now it's log base 1.0538. We've stored it, of 2 equals T. And that's the same thing as log 2 over log of 1.0538 equals T. And when you use your calculator, you end up with T is equal to 13.21. Does that kind of match our guess right here? Oh, it does. So again, it's the same process. We came up with our initial equation we wanted to solve, 2 equals B to the T, so we're doubling it, but we need to find B. And we found B because we knew that after 5 years, it grew to 1.3, 30% greater. So we have 1.3 equals B to the 5th. You take the 5th root of 1.3 and you end up with our B, which we plugged in right there. And then we needed to solve for T. We solved for T, which was 13.21, in this case, years. We can check that because we could take this and raise it to the 13.21 and we should get 2. So the next thing you can do is you can actually use your calculator to find your equation if you are given 2 points. So in this case, we have 120, and 415. So we're going to use linear and exponential regression on the calculator. Let's use exponential regression as the one that's going to be most useful right now. So that's y is equal to ab to the x. So if you go to your calculator and you click on stat and then edit, you're going to put in the points. There's 120, and 415, and then go back to the main screen. Then you go stat, calc, and then you go down to 0. You should see as you scroll down, you can stat 0, as my calculator goes a little bit haywire, expreg, that's exponential regression. And then you hit enter 4 times until it goes all the way down. Don't change anything. Look what it calculates for you. It tells you A is equal to 240 and B is 0.5. A is equal to 240 and B is equal to 0.5. So we know it's going to be y is equal to 240 times 0.5 to the x. A few questions. Is this exponential growth or decay? Well, that's less than 1, so that's decay. Linear would be connecting with a line, but we're just interested in making it exponential regression right now. So let's talk about putting $1 into a bank account that pays 100% interest, meaning you double your money every year. How much would you have if it was compounded once a year, meaning you did this 100% once a year? So you'd start with $1 and then it would grow by 100%. That's your rate right there in decimal. So you'll end up with $2. What does it mean to compound something twice a year? Well, what that means is you're going to start with $1, but then you're going to multiply it by 50% twice. You're going to grow by 50% twice. That's what that is right there, 50% twice. In other words, that's $1 times 1.5 squared. Another way to write that would be $1 times 1 plus the 100%, which is 1, divided by twice a year squared. So if you did this on your calculator, you don't need it, 1.5 squared is 2.25. You end up with $2. Oh, and this should be $2, not $200. $2.25. So we made 25 cents more. So instead of doing 100% once, this means 100% once. We did 50% twice. So what about monthly? Monthly, that would be $1, and that would be 1 plus 1/12, because we're doing our 100% divided into months, which is 12 in a year. And how many months are there in a year? Well, that's going to be to the 12th. You will need a calculator for this, and it comes out to $2.61. So look at that. We started with $2, which is 100% once, and then we got $2.25 if you did 50% twice. And then if you did 1 over 12 12 times. Keep in mind, this is still 1. 1 over 12 12 times is still 100%. And we ended up with 2.61. Will you ever get to $3? Well, let's play around with it a little bit. What happens if we did this daily? If we did it daily, that would be $1 times 1 plus 1 over 365, in this case, to the 365. You need your calculator for this, and you get 2.71456. So you make more money each time you compound it. The more you compound, the more money you make. But will you ever get to $3? Basically, what happens as this gets really big? They have to be the exact same. So you could test it again. You could say, just pick a huge number. 1 plus 1 over, let's say, 1,000 to the 1,000th power. This is where your calculator might slow down a bit. So let's try it. 2.716923. So you made a little bit more, but not much. So do you think you'll ever get to $3? Well, there's a way to find out. We're looking at this right here. What happens as you do the limit as x goes to infinity of 1 plus 1 over x to the x? Well, you end up with the number e. You end up with the number e. We're not going to prove this in this case, but the number e, you can have your calculator spit it out. 2.718281828. It's irrational, goes on forever. Lots of 8s and 2s in there, but it's irrational, which is approximately 2.718281828. It goes on forever. So can you ever get to $3? You can't. So there are some complicated looking formulas here, but the one I really want you to remember is A equals PE to the RT. This is called continuous interest. And that's what happens as this number right here goes to infinity. As you break it up into an infinite amount of small pieces, what kind of interest do you have? Well, you're compounding it infinitely. You're compounding it infinitely. And that's what this formula is right there. P is your principal, that's your starting amount. And then A is how much you have, like the current amount. And then E, that's the number E, and that's your growth rate right there, and T is the time. So in this case, we have P of T equals 100 E to the 0.05 T. So I'm just going to rearrange that a little bit. This is a continuous compound interest because of the E. But one way you could rewrite it is E to the 0.05 to the T power, Now, E to the 0.05 is 1.05127. These are the same. E to the 1 in this is the same. So this question asks, state whether each of the following is growth or decay and find both the continuous rate and the effective rate. Well, we've translated it into our original exponential growth rate, and this right here is greater than 1, so this is definitely growth. This is definitely growth. Well, what this tells us is, see this 0.05 up here? That was the continuous interest rate. That's the continuous interest rate, which is 5% continuous interest rate. But this right here is the effective interest rate, meaning what does that look like if you were just going to do it normal once per year, like once per iteration? And that right there is the decimal part there because it's 1 plus. So it's going to be 5.127%. Continuous is always going to be lower than the effective because continuous is compounded infinitely. What this tells you is if you do this once per year, you get 5.127% increase, which is the same as 5% compounded continuous. So let's do one more of these. So we're going to translate this. This is the same thing. So this is e to the negative 0.025 to the t. I haven't changed anything. I'm just rewriting it. So if you do e to the negative 0.025, you end up with 0.9753099 to the t, Well, this is less than 1, so therefore it is decay. And what's the decay rate? Well, the decay rate, remember, our b value was 1 plus r, and in this case, our b value is 0.9753099. So r in this case is 0.09753 minus 1. So if you subtract 1 from that, you end up with negative 0.024690, keeps going, which means it's going, our decay rate, our rate was negative 2.469%. So what does this mean? It means that if you continuously decay at 2.5%, so this is continuously decay at 2.5%, that's the same as a regular once a year decay rate of negative 2.469.